Okay, so welcome to the Infosys Generic and Random Geometry Colloquium. So today our speaker is Professor Nisheeth Vishnoi from Yale University, where he's the A. Bartlett Giamatti Chair Professor in Computer Science. He has contributed to a lot of different areas: hardness approximation, optimization, sampling. More recently, he also heads the Computation and Society initiative at Yale. Today he's going to be talking about some connections between many of these different areas. So without much ado.
Thank you, Piyush. Thank you. Thank you for the invitation. Thank you for attending this talk. So in this talk, I'm going to show a connection between two different things. One is this world of private optimization, where I come from, and the other is this area of statistical physics, which is a very, very broad area, almost like kind of very difficult to encapsulate what it is. But for people who work in this area, they will see that certain approaches to design optimization algorithms, which are also taking into account the privacy concerns that are emerging as we move into this data-driven world. The design of such algorithms essentially is uses certain ideas and even then contributes to some of the problems in statistical physics. In particular, I will talk about the context of low-rank matrix approximation. I will explain what this is. This is one of the central problems in data science, machine learning, statistics, and so on. And as far as the statistical physics connections are concerned, there will be one connection to what is called the Dyson Brownian motion, which is a very interesting and important tool in the understanding of random matrices invented by Freeman Dyson. And then I will also talk about the so-called Harish-Chandra-Itzykson-Zuber formula, or rather the density, and how these things kind of show up in this world. Just feel free to interrupt if you have any questions or not, something is not clear. I presume the audience here is mixed, and even though I tried to make this talk as accessible as possible, I'm sure I'm assuming many things given my background. So just feel free to interrupt. So let me start by defining the problem. So the structure of the talk is roughly the following. I'll talk about the problem. I will motivate privacy. I will introduce a notion of privacy. And then I will talk about the design of private approximation algorithms. So the problem is the following. You can imagine that there is some matrix which consists of rows which belong to users, different users. And each row consists of what is called a feature vector or a data vector associated to a user. And these numbers here might contain some sensitive information about the users. So that is where the privacy concern will come up. I'll talk about it in a second. But let's first review the basic problem that is studied in many different areas. It's the following. So you first convert this matrix into, or rather look at the covariance matrix of this data matrix, which is just the D cross D matrix, which essentially looks at the correlation between different features. And you're also given an integer k. Let's say it's at least 1. And the high level goal is to approximate this huge D cross D matrix by something very simple. Let's say a rank 1 matrix. So k can be 1. That's already interesting. So to make this problem precise, we have to talk about what it means to approximate M. There is not a single notion, there are multiple notions, and different notions give rise to different optimization problems. So for example, this is a problem that we are going to talk about, the rank K covariance matrix approximation problem. Here, the goal is to compute a rank K matrix that minimizes a given distance to the matrix M. This given distance, for example, could be the Frobenius norm between the two matrices, or it could also be derived by looking at the inner product between the two matrices. So inner product is kind of the opposite of distance. So the more the inner product, the better it is for you. So instead of minimizing the distance, you can maximize the inner product. A related problem is the subspace recovery problem, where we want to approximate this matrix by a low rank projection matrix. So for example, if k is 1, then one thing you could do is just compute the largest eigenvector. So the eigenvector corresponding to the largest eigenvalue, and just look at the rank 1 subspace formed by this vector. And that is, that's the approximation that we would construct. So I'm not going to go so much into applications since I have a fair amount to cover here, but let me just mention that there are many applications of this, and from traditional statistics to more modern applications which involve data which can be very sensitive. Are there any questions about the problem if you haven't seen this before? So the point being that in the classical world where there is no privacy concern, these problems have well-known solutions, they are well understood from a computational point of view, from a mathematical point of view. But in this setting where data may be sensitive, it becomes important to understand how can we do optimization or how can we process these matrices. Can we just release the largest eigenvector of this matrix? The answer in short is no. If you do so, then it is possible to construct attacks which will reveal individuals' private information. And a very famous example of this is the so-called for the Netflix problem. So I don't know if many of you have heard here, Netflix several years ago announced $1 million award for whoever can kind of improve upon their recommendation. So I guess everybody has used Netflix, or maybe many people have used Netflix here. So I mean, like I am spending more and more time just figuring out what to watch than actually watching something on Netflix. So it's clear that the recommendations are not so great. Netflix probably already aware of it. So the way they kind of outsourced this process was to release a certain amount of data for people to play around with. And very quickly, people were able to figure out details of the individual users. Usually, you also need some auxiliary information, which may not be very hard to get, but you can do that. And I guess roughly the reason here why releasing some kind of anonymized data. So, I should mention that Netflix did not include the name of people in this data. And at that time, this was considered a notion of privacy, right? But even moderately dimensional data about people tends to be very unique, and these unique combinations can act as identifiers, right? I think you can imagine your own example, but I don't have to reveal the name of an individual, but I can give 2 or 3 identifiers about people sitting here in the audience that will single them out. I don't want to do this exercise in front of this audience because I want to move on with my talk, but I'm tempted, I must say. Okay, so what about releasing these? So releasing the raw data is a strict no-no. So you can't really release the matrix A. Okay. So what you can say is, okay, how about releasing this covariance matrix that we talked about? Here also there are attacks. In particular, there are these standard examples. So for instance, you can imagine a bunch of people participated in a study, which is checking correlations between your DNA, various sites in your DNA, and the probability to get cancer. Using such studies, using such data sets, if released as such, you can sometimes figure out the membership of a particular individual in the data set or not, in the experiment or not. And that actually can have fatal consequences, not fatal, but significant consequences for the individual, in the sense that if their insurance company figures out this information, then they can check their DNA. I mean, maybe they have access to their DNA or something like that to figure out whether this person will have cancer or not. And that can then affect their ability to be insured in certain countries or not. So like US is one such country where these things are very dicey, I would say. Yeah, so I mean, it's not hard to kind of, once I tell you that it is possible, it's not hard for you to figure out the reason. If there are just a few people in each group and many more these sites, then one can reverse engineer the tables and find out the genetic profiles are. And once you have a genetic profile for people who are cancer prone, you can check with a potential person you are going to insure whether they have that type, and then charge them insurance premium based on that. So you can kind of discriminate based on these things. Okay, so I think I hope I kind of gave you some idea that releasing data can lead to some really problematic scenarios for individuals. So we have to be a little bit careful about the computations we are doing. So we'll go back to this low rank approximation problem in a second, but then let me ask this question, which is a general question. So what can we do? How can we compute whatever we want to compute privately, usefully, and efficiently? So none of these words probably make sense, but probably efficiently make sense. So this means that given the input, we want an algorithm which runs fast in terms of the input length. That's what this means. That's why I've not put a quotation around it. Privately is going to be defined soon. Usefully is also important because one way to be private is to or just output random numbers, right? Yeah, so there is no correlation between input and output. So, but that's not particularly useful. So there is this tension that you can sense already between privacy and usefulness. So I want to release, I mean, scientists are doing all these studies for the betterment of humanity. This data needs to be out there, but individuals are also concerned. And unless their concerns are addressed, they will not be willing to participate in these studies. So there is a genuine need to have useful mechanisms, which are also somewhat where then there is a notion of privacy, which is beyond an individual or a capitalistic company's assurance that your data is private. Okay, that's where one of the key contributions of theoretical computer science has been in the last few years, the introduction of this notion of differential privacy. So in 2006, Cynthia Dwork, McSherry, actually that's Nissim, not Naur. Nissim and Smith gave a paper which tried to define this. And I think they kind of came up with this realization that privacy in some absolute sense doesn't really make sense, but what we can ensure is the following. If we can construct algorithms which have this property that the participation of a single individual doesn't change the outcome by much, that can be something that is not fundamentally blocked and potentially useful. Another thing they noted was that you can't really design private algorithms by deterministically. You will have to have something, some randomization in the middle or in the beginning or at the end. So either you randomize the input or you randomize the output or you randomize the computation. That's what I'm referring to here as the randomized sanitizer. So once you add randomization, even for data which is deterministic, the output is a probability distribution. And roughly speaking, their definition says that if in the data set I change one individual by another individual, the probability distribution output by this randomized sanitizer does not change by much. So in some sense, this is a stability property of the algorithm. Not all algorithms are great. With respect to privacy, we need to design algorithms which are somewhat stable to that. So one algorithm which is completely stable is to just output a constant, I mean, like just the fixed number, but then that is not very useful, as we discussed. Okay, so I just want to show you the definition of differential privacy. This is a high-levelish talk, so take it with a bit of salt. It's not necessary that you understand all this stuff. Yes. Yeah. So yeah, I understood the question. So the question is, how do you measure usefulness? That will depend on the context, and really, even in the same context, you can measure it differently. So, for example, in the low rank approximation case, there is a matrix you would output. So you're given this input matrix M, and you're required to output a rank K matrix. So there is a correct answer for this problem. But you will not output this, because this can reveal privacy of individuals. So you will output something else. So you can measure the Frobenius distance between these, or there are other ways in which you can measure. I mean, in the world of matrices, you can define distances in many ways. But if for different problems, it could be different. So for example, if it's just a bunch of people here, and let's say I want to compute the average age. So that's just a number, right? So I can compute that. There's a true age, but I can also kind of do something to the ages of individuals and then process it. I come up with an approximation to that. And in this case, the answer is very simple, because these are two numbers. So, the distance between the two numbers is a notion of usefulness.
One thing that is necessary, that if a lot of data changes, then the answer should also change. Whereas if one person changes, the answer should not.
So yeah, so it's a very good question. And I'll answer this in a second. I'll address that in a second, not answer that in a second. So the picture is worth 1,000 words. I mean, you have two data sets, and D1 and D2, and let's say A1 and A2 are the corresponding data matrices that I showed you. And let's say this MathCal A is this algorithm that we are looking for. So the definition doesn't come with an algorithm. Definition allows you to tell whether an algorithm is good, private, or not. But there are two parameters in there. One is an epsilon and one is delta. The epsilon one really plays the role of a multiplicative error. So think of e to the epsilon as 1 plus epsilon. So it is saying that the two probabilities point-wise are within 1 plus epsilon of each other. Okay, so a simpler way to write that, if there was no delta, so if delta was 0, then all we are saying is that two probability distributions, let's say Px and Qx, so we want these densities to be close at every point. So this number really behaves like 1 over 1 plus epsilon, and this number behaves like 1 plus epsilon for small values of epsilon. Okay, so this is when there is no delta, but you can also allow an additive violation. So we will look at both. The notion where delta is 0 is stronger. And to kind of answer Piyush's question here, this is a perturbation with respect to one member. So now if two data sets differ by k people, k individuals, then you can use this to get a bound like this. So this is called composition. So there are many nice properties about this definition. One is composition. The other is projection, that once you look at this output, once I give you this output, the algorithm's output on a data set, no matter what you do subsequently with this, it cannot violate the initial privacy condition. I mean, by no matter what, I mean that you can't now on the side reveal the data set, but you can keep applying functions onto this. It's not going to change the guarantee or even weaken the guarantee. So the key question here, of course, is that, okay, this is the definition. Well, there you can poke holes in this definition as well. I mean, as I said, this is not this doesn't say that I cannot get information about individuals. All it is saying is that the addition or change of one individual in the data set doesn't change the probability distribution. The probability distribution itself might reveal the information. So if I have a class I'm teaching and I see that every person in that class has posted on Facebook that they have gone to some party the night before the exam, and if your photo is somewhat not there, so it doesn't really, I mean, it doesn't really preserve your privacy in the sense that, so you see the point, right? That it's not saying that your information is private. It's saying that your contribution to the privacy is controlled. That whether you are in the data set or not in the data set, the outcome would not have changed by much. So it's not a very profound definition in some sense, but currently it is the best definition that we have. There are many, many issues with this definition. For example, one I can tell you is that, so suppose you participated in this study for cancer, the correlation between genes and cancer, and you signed up, you got paid, you don't really even care whether your privacy is really, but maybe now, let's say your brother or your sister, they did not sign up for this study. The fact that it comes out that you have susceptibility to certain type of cancer has direct implications to your sibling because you share DNA with them, right? It doesn't control all this this kind of stuff. Let me just be clear about that. So as such, the area of privacy is very, very important, and this is one thing. The positive thing that I can say about this is that many companies now have adopted this this notion. I'm aware of, like, I mean, all the big tech companies are using this notion. There is no way, I mean, like in many things, mathematics, there is no way to guarantee privacy. I cannot, without a mathematical theorem, I cannot just kind of look at a computation and say, yeah, this is private. It has to come with a mathematical theorem, which is just like an algorithm is correct, the algorithm is private is also a theorem, will be a theorem. And that is why I think theoretical computer scientists are probably the ones who are leading this effort. This is not an empirical science. Yeah. Okay. So let's go back to this this thing here. I'm making the problem a little bit more precise. So going back to this private matrix approximation, I want to talk about the notions of utility. And there are, okay, so first of all, I consider a slightly more general problem, which is given a symmetric matrix M. So symmetric matrix has real eigenvalues. Okay, that's the only place where I'm using symmetric. It could be Hermitian, that's fine. So this is a matrix M with eigenvalues, let's say sigma 1 to sigma d, ordered in this decreasing manner or non-increasing manner. And I'm also given some eigenvalues, some input eigenvalues, lambda 1 to lambda d. And what I would like to really solve is the problem, a more general problem, is to look at the set of matrices which have eigenvalues lambda 1 to lambda d. So this is the orbit of lambda 1 to lambda d under conjugation by unitary matrices if it's complexes, or orthogonal matrices if it's real. And what I want to approximate is on this orbit. So this is this orbit corresponding to lambda 1 to lambda d. And this is the matrix M, which doesn't lie here. I want to find the closest point in some way to measure closeness. Okay, so that's what all this math is saying. In case you have difficulty like me reading notation, and then there are two different ways in which you can measure. One is in terms of the Frobenius norm, and one is in terms of the inner product. It's not really crucial that you understand these formulas in this talk. I mean, I think focusing on the high level is good. It also helps me in the way that you don't spot all the typos in my slides, which I'm sure there are. So how are the rank K covariance approximation and subspace recovery problem special cases of this? In the rank K covariance approximation, I would set lambda i's to be equal to sigma I, which are the desired eigenvalues. And for 1 to k, and rest are 0. So the orbit corresponds to just sigma 1, sigma k, and 0, 0, 0. So I want to look at the orbit generated by this diagonal matrix. In the subspace recovery problem, it is just 1, 1, 1 k times and 0 other. Okay. So I'm using the word orbit without properly defining it because it will be defined in a subsequent slide. So, but it's already good to think about, group actions and stuff if it's something that you have not thought about before. So the Frobenius inner product, if you simplify this a little bit, is, as I mentioned earlier, is what it wants is for you to find the matrix X in the space of rank K projections. So this P sub K, this math calc P sub K is nothing but all the matrices U, EK, U star, where U is in the unitary group and EK is this matrix, diagonal matrix, which is K 1 times and zeros everywhere else. Okay, so sorry, it's not very clear, but that's what it is. So actually, this is an optimization which is linear, but over a non-convex set. I want you to note that. The space is not a convex set. But yet somehow we can solve this. I know the answer to this. I know the answer to this optimization problem. It is the matrix which is, yes.
Every point in that set on the boundary of the convex set of that set.
Not necessarily, because just looking at the density, if I have just rank 1 matrices, right? Rank 1 projection matrices, the convex hull of that is the space of all of these so-called density matrices, right? Which are trace 1 positive semi-definite matrices. But the boundary will also consist of rank 2 and rank 3 and so on.
That's not can these be in the interior of the convex set?
Oh, do you allow them to be in the interior, or what is the?
Are they? Because otherwise you do convex optimization on the convex.
You can, yeah. Yeah.
So even though it's not convex, you can effectively use convex optimization. You have a oracle for the convex.
But why would that go on the boundary? And that's what I'm saying. There are more things on the boundary than just so effectively you will have to prove that the optimal solution. So you're looking at a relaxation basically. So what I think Hari here is suggesting is to maximize this inner product X and M, where now X is in the convex hull of PK, which is the same as the set of all density matrices actually. Trace K density matrices. Also, these are not density, but trace K density matrices, right? So you find some point here. You still have to show that the optimal solution will be. Yeah, it's not hard. I'm saying it is hard. Yeah, but I think so the point the reason why I'm saying, so the reason why we are able to solve this problem is not just because of convexity. It's about because of symmetries. It's because this orbit has, this object is an orbit. And that is the reason why we are able to do this. We can't, I mean, if I change this body orbit even a little bit into something which is not an orbit, then it's not clear how to do it. So this classic Schur-Horn theorem, which you probably know very well, right? It uses this equivalence between the unitary group and the Weyl group of that, the symmetric group, and so on. I mean, so there are, you can of course explain this to an undergraduate without any reference to all this stuff, but there is a deeper reason to do that. So the reason why I'm saying, okay, so in the classical world, all you want to solve this problem, and this is easy in the sense that it can be solved by an efficient algorithm. The question will arise how to design private I mean, like now we can't really, we don't want to solve this problem. So what do we do? So I want you to think for a moment, and I mean, so far I haven't used any idea from statistical physics. So you might be wondering what the speaker is just misled us into some talk. So I want you to think for a moment and see what would you do if you were, let's say, a physicist or a mathematician, and I said you can't really output this, the solution to this. So what are potential ideas that come to your mind without looking into the future? Add noise to M. Who said that? Oh, you said that. Okay, yeah. Yeah, that's a valid idea. Yeah. And then do what? Yeah, that is one of the approaches. Correct. So that's when you're adding noise to the input and then solving the same optimization problem. What other ideas come to people's mind? So there is one very basic thing that everybody in statistical physics would know. It's a Gibbs density, right? People have heard of it, or yeah? So instead of maximizing something, you could produce a sample from the corresponding Gibbs measure at some temperature. Okay. So what do I mean? Well, this is, I guess this is how statistical physics started to think. You have some function f, which is, let's say, some energy which captures the energy of a system, right? What this is trying to say is output the state which has minimum energy or max, whatever, yeah, minimum energy, right? Instead, what you could do is do something like this to output an X with probability proportional to this corresponding Gibbs density. That's a reasonable thing to do, right? I mean, that's also adding noise in some more complicated manner. So what is the difference between what you suggested, which is to add noise to the matrix and then then solve this problem and sample from this? What's a qualitative difference that you can imagine? So I already told you one strategy, and you have to kind of believe me that something like this will work to obtain privacy. That should already be exciting to people who love these kinds of things. That instead of optimizing, now you're going to sample. As we already discussed, that there is no way to kind of deterministically solve this problem. So you will have to introduce randomness. And Hari here already took the easy one out. So it's the harder one. You get back F? You mean you get back the optimizer? Yeah, so this is, I mean, so this is like the, this is related to the temperature parameter. So it spikes up. Yeah, right, exactly. So that's In fact, there is a very direct correlation between beta and the privacy parameter epsilon. So let me just show you that. It's a two-line proof, but I'm not going to do it here. This is called this exponential mechanism. And the result says that, well, okay, I mean, people didn't just write this. I mean, they did more. All these papers did more than this. But here is what is the relevant part for us, is that if I look at this density now, e to the epsilon times the inner product. So this was the function I wanted to maximize. And this is a density on the space of, in this case, the space of rank K projection matrices. So you have to believe me that there is a measure that you can put on there. Okay, if you have not seen that before, this is true. It's a nice. So PK is, I mean, that's, yeah, so this is a very beautiful object. It has many, many properties actually, which are somehow all implicitly being used here and there. So one of them is that you can associate a measure to this object. It's a very basic fact because the unitary group has a measure. So it can inherit a certain measure from the unitary group. So you can do probability on these manifolds. Okay, you can, there are also algebraic varieties and so on, but that's not going to become important right now. So, okay, so this is a well-known connection. This is nothing to do with me. This is many, many years ago, 10 years ago, people realized that there is a connection between sampling from the corresponding Gibbs density versus doing private optimization. And all I'm doing is just plugging in the function that I was interested in. That's all I'm doing. These results are more general than that. And the real question was, how do you sample efficiently from this? So now going back to Hari, right? I mean, that you said that optimization is easy. But now we have this orbit and I have a density on this orbit. How do I give an efficient algorithm to sample from this? So this was, none of these people were able to do this. Okay. So it turns out that this I already told you that these are orbits. So this is, let's skip that. This is the more general sense in which you can define a unitary orbit. So you have to take any diagonal lambda and define this thing by conjugation. So the problem that I'm interested in is how do you efficiently sample from this orbit? Now you can say, okay, you know, you're interested in this question. So what shall I do? I'm a statistical physicist or I'm a mathematician. I don't care about this. It turns out that this is actually exactly the density that has been studied by these people, Harish-Chandra-Itzykson-Zuber. It arises in at least a dozen different contexts in mathematics and physics. And while these people proved how to compute the partition function. So that's an integral over the unitary group. It's called the HCIZ formula. And in fact, even more general formulas than this were known already in Harish-Chandra's work from the 50s for general Lie groups, more general Lie groups. The problem of sampling from this density was not known. So that is the question. So what is the relation between this and this? Well, so in this density of the HCIZ density, this is a density on the entire unitary group. This is a density on the orbit. But if you kind of choose one matrix in the HCIZ setting to be the descriptor of the orbit, and one matrix to be the matrix corresponding to the linear functional, you recover this very straightforward connection. There is nothing, this is completely straightforward. And you can choose which one to make the orbit and which one to make. So how many people have seen this this thing here? Okay, so it's a few. Okay.
If explain that to be your imaginary private access or whatever you're going to say.
Well, then the privacy would be imaginary, I guess. Because no, I understand. Yeah. I don't think so. But I don't want to kind of say confirmatively that that is the case. I never thought about the imaginary case. So this is the problem. How do you sample from these efficiently is the keyword here. And efficiently in a very precise theoretical computer science sense, where you're given these input matrices, you want a polynomial, and you will be, well, first of all, you will never be able to sample from this exactly. So I'll also give you an error parameter. And so I want you to output a density, a sample from a density which is close to it. So this is the theorem from 2021, which makes this precise, that given these Hermitian matrices, lambda and y, we give an algorithm to approximately sample from this density within an error of this psi. And the running time is polynomial in the norm of y, the norm of lambda, and log 1 over psi. And this distance, when I say within error, it is an error of this type. It's much stronger than total variation distance. Total variation is not enough to establish bounds like this. So it's a pointwise. Okay, and they have many applications, well, to private low rank approximation, to HCIZ densities and statistics. People have looked at what are called matrix Langevin distributions, spherical distributions. This was an open problem there. And I think finally, I came to it via an earlier paper of mine, which was looking at maximum entropy distributions on unitary orbits as a solution concept to do quantum inference, to infer quantum states from density matrices. Okay, so while I could show in that paper that we can compute these entropy maximizing densities, I did not know how to sample from that. So that is where I was coming from this. Yeah, I did not realize that this is let's start working on HCIZ density. That was not the thing. Okay, so I have 15 minutes. I will just quickly show you what goes on into the proof of this. Yeah.
So, the algorithm more general in the sense that if you were to replace the Frobenius law of yx by, suppose you could do, I don't know, a certain task efficiently, then you can sample according to a related error.
No. It uses like everything about this orbit. So yeah, so that's what I want to show you so that you kind of believe me. So let's first look at how do you sample a random unitary matrix. So one way to do that is to pick a random Gaussian vector in d dimensions, normalize it, it has unit norm, a complex Gaussian vector. So you normalize it as unit norm, and now work in the space orthogonal to it. So that is easy. There's something should be able to do. So you can sample a random point on the unitary group using this idea. The issue is that once you add this exponential density everywhere, you break this symmetry. So it's not clear what to do. And moreover, as I mentioned, that this is an algebraic variety of a high, generated by high degree polynomials. So there are very intrinsic correlations between the entries. So yeah, it's not clear how to extend this simple naive idea. And so So one of the key ideas is to view the matrix itself in terms of eigenvalues. So a matrix on this orbit, but then you will say, okay, but all you're doing is conjugating a given matrix by unitaries. So all the matrices have the same spectrum. So what are you even talking about? So let me tell you what I'm talking about. So what I'm going to do is to look at all principal minors of this matrix. So the 1 cross 1 minor, the 2 cross 2 minor, and these are the leading principal minors. So the ones that are to the left and up. And I'm going to write down the eigenvalues in decreasing order for all of, so for example, all of these blocks. So these 3 eigenvalues correspond to the big yellow block. These 2 eigenvalues correspond to the 2 cross 2 block, and this corresponds to the 1 cross 1 block. And I'm writing them down in decreasing order for a reason. I know that because this is the whole matrix, these numbers are the same as the given lambdas. Okay? But now the intermediate things are not straightforward, right? These numbers are not lambda i's. I mean, these are something else. So that is where some new information is coming up. So this is a nice exercise if you want to give to your students, is to show or to figure out what can you, from this information, what can you recover about the matrix. If I take this matrix X and give you these eigenvalues, what can I get back about? Can I recover it completely? Probably not. I mean, these are less numbers than the eigenvalues. Okay, but it's quite remarkable, and this just requires basic linear algebra to prove that you can essentially determine all the entries of the eigenvectors to a complex sign. Once you know this, yeah, you can figure this out. There's still some information missing, but that's the phase, and not the. This map is called the Rayleigh map, which takes a matrix and maps it to these numbers. So some very nice properties of this map are what is called interlacing, which follows from Cauchy interlacing. Then that's why I've written it in this weird manner, that this R12, for example, will be in between R13 and R23. That's these basic interlacing theorems. So in fact, all the inequalities that you see here have this property that if I now look at the entire orbit, which is some non-convex object in n square dimensional or d square dimensional space, right? And I map and look at the image of this object with respect to this Rayleigh map, and actually I get a polytope here, a convex polytope. And the inequalities that are necessary to describe this polytope are already listed here. So here are some facts. So this image of this orbit is a polytope. It's called the Gelfand-Sethlin polytope. So you may say, okay, fine, it's interesting, but there are many convexity results like this. Something that I think is non-trivial and is not true for other moment maps is the fact that the uniform measure on the orbit pushes forward to the Lebesgue measure on this polytope. For other moment maps, what you can show is that it still pushes, if the image is still a polytope, but the measure is piecewise polynomial. So if you use this Duistermatt-Heckman theory to kind of, if you know it, you know it. If you don't know it, you can ignore my comment. But this is a rather surprising fact, that the uniform measure pushes forward to the uniform measure on the polytope. And in fact, you can also show that this log linear density on the orbit pushes forward to a log linear density on the polytope. So these are purely structural theorems which use everything about the symmetries that generate this orbit, and there is no chance that this will work for like general manifolds. Okay, so now the algorithm is kind of relatively simple. Once you make these real connections, you say, okay, so first you sample a point from the exponential density on this Gelfand-Chatelain polytope. How do you do that? Well, this is one of the major achievements of all of theoretical computer science, is to sample a point from a polytope. This is not a trivial task, but it has been done by people like Dyer, Fries, Kannan, Loash, and others. The culminating piece of work is that you can execute this first step. And then once you have that point, we still have these fibers, because this is not a one-to-one map. There are all these fibers. And so you have to pull back this point to a random point on the fiber, and that can also be done. So the rank one sampling algorithm looks somewhat simple. The GT polytope actually in the rank one case, the P1 case, turns out to be just a probability simplex. So you have this log linear density on the probability simplex, you sample from it. You then going back is just described by this process. So hopefully you got a flavor of the proof. I want to spend 5 to 7 minutes on the next part, which is the strategy that Hari had suggested to introduce a different connection to statistical physics. So the first part of this talk, we showed that by viewing a certain problem in private optimization leads to some new algorithm for people in different areas. Here we are going to do the reverse. We are going to use some very nice ideas from statistical physics to analyze this method that Hari had proposed, which is to add noise to this matrix and then compute the top k eigenvectors. I mean, you can ignore all that, but that's really what is going on. Okay, so let me draw a picture here for you. So this is the space of matrices. This is your input matrix. This is the manifold on which you want to project. So this may be the optimal point, let's say A. But now you're adding some noise and you move to some matrix M hat and you project this to some A hat. So what I want to bound is how much do they differ in some Frobenius norm or something like that, right? So that is the real question. The starting point of this work with Oren Mangubi is the realization. It's completely trivial, but somehow it was not done before because it's, and you will see maybe why, is that this thing here you can view as just Brownian motion in this space. Okay, so you'll say, okay, so what? Well, the reason to so what? Because I mean, the reason that why this viewpoint is helpful is that we figure out that you can write down this error in terms of integrals of how eigenvalues and eigenvectors are changing with time as you're adding noise. So we needed some equations for motion, stochastic equations of motion as to what happens to the eigenvalues of the matrix M as you go from M to M hat, and also eigenvectors of this. And fortunately for us, Freeman Dyson had wrote a paper in the 60s which wrote down exact equations of evolution of the eigenvalues and eigenvectors, which I must say is really amazing. So the upshot is that we can get bounds on the utility, which is the difference in Frobenius norm between these two quantities in terms of integrals over these stochastic equations. And the thing that starts mattering for people who are familiar with these equations, this is also called the Dyson Brownian motion. This is a matrix Brownian motion. And basically, Dyson wrote down equations of the form d lambda I by dt is equal to something which is a drift term plus something which is the noise term. And the key thing is that there is a repulsion. And I'll show you these equations. that as two eigenvalues start coming close, they tend to repel each other. So in some sense, the first picture that I showed on my slide, the right-hand picture, which showed all these paths, I don't know if anybody noticed that these paths don't intersect with each other. This is a property of Dyson Brownian motion, that these are non-intersecting stochastic processes. And in fact, what becomes crucial is how close these things can come to each other. So we need that these two things can never come close enough. So we need to make an assumption, which is that the starting matrix M has gaps in the first k eigenvalues. Okay. This assumption we observe for many data matrices, it is true. It is a reasonable thing to ask if one doesn't need to make this assumption. And that's a valid question. But assuming that, we could improve upon the previous works of Dwork and others in pretty much all the problems that they looked at. They were using standard for matrix perturbation bounds, which are in some sense worst case, in the sense that, okay, so you have a matrix M, you have another matrix M hat, you want to understand how much these changes, but they don't use the fact that this M hat is actually generated by a stochastic process somehow. They use these Weyl type inequalities or Davis-Kahan type inequalities. Whereas we can get a better handle on these quantities because of having a more explicit understanding of how the eigenvalues and eigenvectors are changing. Okay, so if I should definitely show you what these equations look like and show you the picture again. These are the equations. And as I said, that there is this term in the denominator which causes this repulsion between these eigenvalues. A lot of theory in random matrix, in the random matrix world and in this SDE world consider the case where M is the zero matrix. So we had to do some extra work for this setting when M is not the zero matrix. So this is the case of zero matrix where all eigenvalues start at 0. So you start at M equal to 0. And you see how the eigenvalues are diverging. And if I just want to flash the proof, I mean, just the steps of the proof. I mean, yeah, so you do some integral over certain potential functions, and yeah, you can, yeah, I mean, you have to kind of believe me at this point that this way of looking at things is useful. Okay, I don't have time to explain this, but hopefully I have given you some evidence that there are some interesting and non-trivial connections between these two areas of private optimization and some sub-areas of statistical physics. In the one direction, motivated by a problem in private optimization, we came up with an efficient algorithm for a problem which is important in many areas, including statistical physics. And in the second result, which I had less time to go over, I talked about how we can use these sophisticated ideas such as Dyson Brownian motion and its connection to random matrix theory to analyze a very basic process of adding noise. The difficulty, I mean, you know, it's yeah. So what I mean, you know, so the difficulty, Dyson Brownian motion has been around for many years, but the difficulty is really in looking at their projections. So it is not clear to me what is this thing here. So this also is some stochastic process from A to A hat. This is a low rank approximation of this matrix. So there is this mapping is fairly non-linear and non-trivial. So it is not at all obvious what is the right way to add noise in this setting. So one of the questions that you can ask is if we can directly work over this domain and figure out a way to add noise. And that's where people who have more geometric insight can maybe contribute. A natural question is whether we can remove this assumption of large gaps. This is something we have been able to do in upcoming work with Oren Mangubi. But that is requires some new results in random matrix theory, which were not known before. So I'm happy to talk about it offline. So I guess the general connection seems to me to point to this kind of developing a theory of how to add noise, where to add noise and how to add noise. I said you can add the noise in the input, you can add noise at the output, or you can add noise during kind of the computation of the functions. All of these are so I suspect there are a lot more ideas from this community which generally studies systems which have stochastic evolution to be useful in this area, and I would like to thank you for your time and attention.
If there are any questions.